Hi there, I'm Aphelion. Welcome to the Ephemeris podcast where we delve into the world of astronomy weekly. Thank you for joining me on the sixth episode of what is now the new chapter in the new season. It's going to become not so new and not so um, novel, I guess, in a couple of episodes, in which case I might have to alter the intro a little bit. But for those of you who have not been following the podcast so far and are new here, every week we pick out three articles to look over that tell us a little bit more about the universe around us. And so, without further ado, we should get into what the three articles we're going to talk about today are. So, the first article we have lined up is about the quasi-moon of Venus, which is now called Zoozve or Zoozve. The second article is about galaxy collisions and tidal tails and sort of the research that's going into that. And the last article we'll have to discuss today will be the discovery of a pulsar in a supernova. So, first article, Zoozve, very interesting name for this quasi-moon, whatever that is, of Venus. We're going to get into all the details of that right here. So, the last time we talked about planets was in the Carl Sagan episode, and we talked briefly about Venus's surface and atmosphere. But I do want to allow an opportunity to talk a little bit further about Venus, or a little bit more about Venus. Because why not? Given the opportunity, might as well do it right here. So, most people know that Venus is the second planet from the Sun and similar in size to the Earth. Venus spins opposite to the Earth, which is known as retrograde motion, which I assume is very common knowledge, but maybe that might be news to some people. Venus spins very slow, actually, because its sidereal day is 243 Earth days, while it takes, I think, 225 Earth days to actually make one orbit around the Sun for Venus. So its sidereal day is actually longer than its year. Venus has the most massive atmosphere among the terrestrial planets, which I will say Venus's atmosphere is a whole topic in and of itself. I could literally spend a third of one of these episodes just picking out an article about Venus's atmosphere and going on and on about it. But we're not going to do that here. I just want to give a brief description of Venus. Venus also has no seasons because of its minimal inclination of orbit. For Venus, I believe it's 3.4 degrees, while Earth's is about 23. So a huge difference there that's not going to create seasons. Or there's a huge difference between Venus's and Earth's inclination of orbit, and given that Venus's is so small compared to Earth's, obviously it's not going to have seasons. So, in terms of the history of Venus, we know that it used to be an ocean planet, but there was a runaway greenhouse effect that occurred in the planet, and with such a big atmosphere, that all happened, and all of the existing water evaporated. So now it's a very, very hot planet with temperatures between 800 and 900 degrees Fahrenheit, or somewhere in the 400 degrees Celsius range. So, yeah, I think the whole history of Venus being an ocean planet is interesting, because if that were still the case, then the conversation around space travel would be very, very different, right? We wouldn't have to worry about sending probes to Venus, because we might actually be able to send humans there, just because of how much more habitable it would have been. So, that's a little bit about the history, and actually something else I should add on. On top of Venus having a similar mass, size, and density to Earth, it might also have a similar chemical composition because of the history of the formation of the solar system, which I'll just briefly go over here. The nebular hypothesis, which is the leading theory for it, states that when the Sun was in its protostar phase, and in fact it was a T-Tauri star during that time, and it was carrying a protoplanetary disk, there were planetesimals forming more than 4 astronomical units beyond the Sun with high melting point elements like iron, nickel, and aluminium. 4 of them being Mercury, Venus, Earth, and Mars. So that would give reason for whatever's really at the core of Venus to be similar to what's at the core of the Earth. The most important characteristic of Venus that we're going to talk about today, though, is the fact that it has no moons. And there's a very important caveat, which our first article addresses. So, in November of 2002, Brian Skiff discovered the first quasi-moon, or quasi-satellite, belonging to Venus at the Lowell Observatory in Flagstaff, Arizona. A quasi-satellite is an object that essentially orbits the Sun at the same rate that its companion planet does, but with a higher eccentricity than its companion planet, which means that the movement of a quasi-satellite seen from the perspective of the planet by an observer facing the Sun looks like the satellite is orbiting its companion planet, or making loops around it, I would say. Like something visually that looks like, a loop. So I know that's a lot to digest in word form, but if you happen to come across a simulation of a quasi-satellite, you'll really understand what I'm talking about, and it's a lot less complicated. But if that first explanation is still a bit disorienting, I'll tell it to you in a different way. If you're an observer of the Sun, the Earth, and one of its quasi-satellites as a system, and you followed the Earth as it orbited the Sun, the quasi-satellite would look like it's making these weird shaped loops around the Earth. So almost as if it's orbiting, but not quite, because it's actually orbiting the Sun. And so, yeah, that's pretty much the best I can do to put it in verbal form, because there are some visuals out there. But we are a podcast here. So that's all we need to know about quasi-satellites and the discovery of one belonging to Venus. So, because of this discovery in 2002, Venus has no moons, but a quasi-moon. Now you might be saying, I thought we were supposed to be looking into current news. This sounds like old news. Well, yes, but there's something new about the quasi-moon, and that's its name, which has a funny story to it. So, sometime after the discovery of Venus's first quasi-moon, named 2002 VE68, an artist named Alex Foster made a solar system poster including the quasi-moon. However, he made an error when writing the name on the poster. He copied the name down as ZOOZVE instead of 2002VE. So, the name that was copied down onto the poster would sound something like Zoozve or Zoozve, instead of it being 2002 VE. This error came into the limelight after Radiolab podcaster Latif Nasser took a closer look at one such poster he had in his son's bedroom. And after extensive research and talking with people who had experience at NASA, he got to the bottom of the simple copying error, which I just described, but wasn't figured out until, Latif Nasser came in and did all the research for it. But this was not the end of the story, as is kind of indicated by the title of the article, because Nasser actually asked Brian Skiff to propose making the name of the quasi-moon Zoozve, or Zoozve, which actually took some convincing. I won't get into all the details. But on the 5th of February 2024, the International Astronomical Union officially named the quasi-moon Zoozve. And it's a bit of a break from the conventional naming schemes of the International Astronomical Union, because they like to choose mythological names for the objects and wouldn't necessarily be interested in putting some random Zoozve artist air name in there, because I mean, ultimately the vote was quite narrow and it did manage to get through, but this is definitely like a very, very one in a million event, I guess. And so some more facts. I don't know how I got vax there, but more facts on Zoozve. It has been a quasi-moon of Venus for 7,000 years, but will leave its orbit in 500 or so years, because quasi-moon orbits tend to be quite unstable, and if there's just even a minor disturbance between the whole system of the quasi-moon, its companion planet, and the sun, then it's gonna leave orbit. And the original name for Zoozve follows a naming pattern, actually, which starts with the year of its discovery, 2002, which might have been very obvious. But the situation with VE68 has it has a pattern to it. So the first letter of V signifies the half month in which the object was discovered. So the first half of January would be given an A, and the last half of December would be given a Y, where I and Z are removed for convenience. The second letter, which is E, and the subscript number, which is 68, are designated based on the order of their discovery. So 2002 VE68 would be an object somewhere in the 1700th order of objects discovered in early November, and an object that was discovered in 2002. So yeah, that's a very complicated reasoning for the naming scheme, and personally, I do actually prefer Zoozve and some of the mythological names, because I get the universe like needs a taxonomy that organizes all of these huge and even really small objects, but I just don't get why you have to name things with so many numbers. Like there are objects out there. I was just like randomly looking into old stars, a list of just old stars and old stellar systems, and you come across names like SMSS J0 31300.36 dash 670839.3, which is like, that's a long list of numbers that probably shouldn't make a name. I know there's a reason why it's named this way. I couldn't tell you off the top of my head the reasoning, but I know there's a reason. But it just seems like, universe or stellar objects need better names, and I feel like this is quite a nice story of how one quasi-satellite got a unique name. So yeah, no hate towards objects that are named with pretty much numbers, but that's just how I feel. So yeah, that was a bit of a tangent. But that's all I have for the Zoozve story. Our second article today, as I talked about, is going to be about galaxy collisions and tidal tails. And I should preface this discussion of the article with a little bit of a preface for galaxy collisions. Galaxy collisions aren't exactly what they sound like. When two galaxies come together, they don't physically collide like we might imagine a bat colliding with a ball, but rather the structure of the galaxies are completely contorted due to the gravity of both objects. And this is a process that is very complex and takes probably tens of thousands of years, if not hundreds of thousands. But despite the many complexities of galaxy collisions, there's one common feature that seems to come out of them, and that is tidal tails. Tidal tails are long, thin regions of stars that and interstellar gas that are compressed in a galaxy collision, or at least it seems like that based on simulations. These regions spawn huge amounts of star formation and can create stellar nurseries, and eventually these regions can be pulled back towards the galaxies to create an irregular galaxies, but nonetheless, these tidal tails are quite the spectacle when it comes to observing galaxy collisions. And that's where our second article comes in. So, Hubble Space Telescope has been on the lookout for clusters of newborn stars to analyze the star formation of tidal tails. And with tidal tails, we kind of do presume that the age of the stars are quite young, like 10 million years old or less. And so, Hubble's on the lookout for those kind of stars. It looked at 12 galaxies specifically and uncovered 425 young clusters, each cluster containing as many as 1 million blue newborn stars. That is a lot. So you're talking about possibly 425 million blue newborn stars in this long strip of just active star formation created by a galaxy collision. That sounds quite fascinating. And now a team of astronomers have used the infrared capabilities or near infrared capabilities of NASA's Hubble Space Telescope to study tidal tail clusters and determine their ages and masses along with properties of their merging galaxies. The first thing we find out is that based on their data, the stars were actually near 10 million years old, so accurate with what we expect. A quote from the article and talks a little bit more about stellar properties. Quote, "These observations tell us how stars form and what regulates those processes. This knowledge is critical in understanding how stars in our own galaxy were formed," said Associate Professor Sanjayita Borthakur, who is an observational astronomer specializing in extragalactic astronomy at ASU's School of Earth and Space Exploration. Another quote, "Before the mergers, the galaxies were rich in dusty clouds of molecular hydrogen that simply may have remained inert, but the clouds got jostled and bumped into each other during the encounters, and this compressed the hydrogen to the point where it precipitated a firestorm of star birth." So quite some fascinating stuff that sort of the beauty of galaxy collisions in activating these inert gas clouds. And I'd say this article and with these quotes we get a little bit more clarity as to the influence galaxy collisions have on increasing star formation and just how interesting it can be. Some other quotes that I would like to mention that tell us a little bit more about what we're looking at here. "The fate of these strung-out star clusters is uncertain. They may stay gravitationally intact and evolve into globular star clusters like those that orbit outside the plane of our Milky Way galaxy. Or they may disperse to form a halo of stars around their host galaxies or get cast off to becoming wandering intergalactic stars." So sort of the same stuff that we already have a consensus on when it comes to tidal tails. Like they could become a part of an irregular galaxy, or they could really just disperse off and becoming just rogue stars out in outer space. An additional perk to observing tidal tails is that it gives us insight into star formation in the early universe, which is likely triggered by many galaxy collisions. And additionally, because we know that Andromeda and the Milky Way will be colliding in the next 4 billion years or so, perhaps these findings might tell us more about the fate of our own galaxy. And just for the record, Andromeda and the Milky Way colliding is not the most catastrophic event that will happen to our solar system. It's just a matter, again, of it's not a physical collision, but a gravitational sort of contortion that may or may not affect the interaction of stars based on how far apart they are. So, nothing to be worried about in terms of Andromeda and the Milky Way colliding in the next 4 billion years, but just a fact that we might want to take into consideration when we're looking at tidal tails. So, that's pretty much what I got for tidal tails. Very interesting phenomena, I would say. And so, with that, let's move on to our last article of the day, which is about a pulsar within a supernova remnant. I'm not going to waste your time here. We're going to get straight into this article. There's not much to preface the article with or background information, because we have looked at pulsars and supernova before on this podcast. If you're not familiar with these two objects, feel free to check out the season 1 episodes where I talk about them. But yeah, because we've sort of hit it home with those two objects, not much to preface here. We're just going to look into this quite new and quite rare phenomena that we're witnessing. So, astronomers have found a pulsar within a supernova remnant named CTB87. It's the first supernova remnant pulsar detected with the 500-meter aperture spherical radio telescope, which is abbreviated as FAST. Supernova remnants are exactly what they sound like, the aftermath of a star life-ending explosion, and just huge clouds of dust and gas ejected into the interstellar medium. So the supernova remnant named CTB87, which we're looking at here, is a pleionic supernova remnant, which basically means that the remnant is a shell with a pulsar wind nebula within it. The pulsar wind nebula, which is also known as a pleion, is a nebula powered by a pulsar and the wind it generates. So flows of highly charged particles from the pulsar interact with the surrounding interstellar medium, which creates this nebula around the pulsar. The unique part of the pleionic supernova remnant we have here in CTB 87 is that we found signs of a pulsar before we actually found the pulsar. So we found radio waves or emissions and other electromagnetic emissions, but we did not find the source of it. Eventually, in the article, it is mentioned that the team of astronomers who worked on a paper about this, they discovered the pulsar, which is named CXOW J2016 plus 3711. And once again, not a fan of those numbered names, but it is what it is. So yeah, essentially with the article that we're looking at today, it's about a pleionic supernova remnant where we knew there was a radio source and source of other electromagnetic emission, but we had not identified the source, and that's sort of going to be the central idea here. So, as I just mentioned, the paper found the radio source, and we also discovered that CXOW J2016-3711 is a millisecond pulsar with a rotation, or almost a millisecond pulsar with a rotation period of 50.8 milliseconds, and the strength of the equatorial surface dipole magnetic field of the pulsar was found to be 1.9 teragauss. Now, Gauss is a unit for magnetic flux density, where every Tesla, which is the SI unit for magnetic flux, is 10,000 Gauss. So the magnetic flux density of this pulsar is 190 million Teslas. Now, if you don't believe me when I say that this number is astronomically huge, let me give you some comparisons. The Earth's magnetic field is 3.2 times 10 to the negative 5 Teslas. The largest MRI scanner only clocks 11.5 Teslas. The strongest magnetic field trapped in a superconductor only registers 17.6 Teslas, and the strongest magnetic field produced by a non-destructive magnet was 97.4 Teslas. So if you're going to compare 190 million Teslas to that stuff, that is an absolutely huge number. Man. And there's still a lot we do not know about this object yet. this source of radio and X-ray emissions. We're a bit cautious about it. We still call it a pulsar candidate because we're not quite sure, but yeah, it's a very interesting object that we have in the middle of a supernova remnant, which is creating a pulsar ring nebula and therefore a plurionic supernova remnant. It's like nearly the whole system is nearly 44,000 light years away from us, and we still have yet to find gamma ray emissions coming from it. So, some very interesting stuff going on here with this hugely magnetic pulsar once again. So, yeah, that's all I've got for the last article, which means that is where I'm going to end this podcast episode. If you all enjoyed listening all the way through, and I appreciate that you've come this far in the episode, if you enjoyed, make sure to leave a follow on Spotify if that's where you're listening. If you're listening on YouTube, make sure to drop me a subscribe so that you will see all future content. And yeah, feel free to like, share, comment on any thoughts you have. And until the next episode, I will see you all later. Peace.